Hi everyone, so section 11.4 is all about polar coordinates, and I'm going to start out with a basic example. We've got the point -1, 1. Now this point is written in the standard coordinate system that we're used to. -1, 1 is written in rectangular coordinates. Rectangular coordinates. Rectangular coordinates are also called Cartesian coordinates. You might also hear that. And what rectangular coordinates do, if we really want to think about it, you guys are already familiar with these, but the first number tells me, okay, starting at the origin, how far to the left or to the right am I going? Negative number means I'm going to the left. Positive number means I'm going to the right, so the -1 means starting at the origin, I go one space to the left. Second number tells me how far up and down I go. Positive number tells me to go up, negative number tells me to go down. So go one to the left, one up, and there's my point. You guys have been doing this since basic algebra. Now, polar coordinates, instead of telling me how far to the left and how far up I have to go, polar coordinates tell me, okay, starting at the origin, how far out do I need to go? So we call that letter R. And what direction do I need to go? So how far out and then in what direction? So what do I mean by what direction? I mean what angle in standard position. So if I start from the positive x-axis, I'm talking about this angle theta. That's going to be the direction in which I'm traveling from the origin to get to my point. So r comma theta in polar coordinates. R tells me how far from the pole. In polar coordinates we call the origin the pole. So how far from the pole. And theta is going to tell me in what direction am I traveling. So what direction. So if I want to convert this point -1, 1 into polar coordinates, I just have to remember some basic trigonometry at this point. So I'm just going to do what we've done several times before in this course. I'm going to draw the right triangle and the reference angle. So you should recognize the triangle that I've drawn as a 45, 45, 90 right triangle. Right? Both legs have side length 1, and that should tell you that the hypotenuse, what we called r in this picture, is going to be the square root of 2. And since we're looking at a 45, 45, 90 triangle, this angle's 45 degrees, which tells me that theta is going to be 135 degrees. Now this is pre-calculus, so we want to talk about radians wherever possible. So instead of 135 degrees, I'm going to call that 3 pi over 4. And theta equals 3 pi over 4. So what we've done here is we've converted the point -1, 1 from rectangular coordinates into polar coordinates. So -1, 1 in rectangular coordinates, I'll just denote that with an r, is going to be the same as square root of 2 comma 3 pi over 4 in polar coordinates. So a couple of key relationships that we want to derive from this example between rectangular coordinates and polar coordinates. Let me get rid of a couple of things here. And let me just draw a general point put it in the first quadrant just to make life simpler. So this point, I'm going to call this x comma y in rectangular, and r comma theta in polar. So remember, the rectangular coordinates tell me how far to go out to the right and then how far up or down to go. And then the polar coordinates tell me how far away from the pole and in what direction. So my r and my theta. So what we want to do is we want to derive a few key relationships between xy and r theta from this. So the first one, the most obvious relationship, is the Pythagorean theorem. R squared equals x squared plus y squared. And if I look at the angle theta, its tangent is going to be y over x. Now, if I look at these two equations, notice that the main players here are r and theta. If I switch my point of view and I think about x and y, if I want to find what x is, I can think of x as r times the cosine of theta. And just to break that down a little bit, remember cosine theta is adjacent over hypotenuse, so if I want to write that out, I want to write that out really clearly. Cosine of theta equals x over r. So I'm just multiplying both sides by r here. And likewise, I can write that y equals r times sine theta. And those are the four key relationships between the rectangular coordinates and the polar coordinates that we'll use again and again throughout this section. So we'll take a look at a few more examples here in just a moment. Alright, so this is a fancy schmancy document camera that I have now that no one's allowed on LCCC's campus because of the coronavirus. So anyway, this is theorem 11.7 on page 922. This is the same set of relationships we just went over on the whiteboard relating x and y with r and theta from rectangular coordinates to polar coordinates. So you can see those there. What we're going to do now is go over a couple of examples where we just take a look at graphing, become a little bit more comfortable thinking in polar coordinates. No, I'm not looking at a spider web on my document camera here. We're looking at, this is polar graph paper. So typically with rectangular coordinates we have, no surprise, a rectangular grid for the graphing paper that we use. For polar coordinates, remember if we're thinking about r and theta, and maybe I'll work something better with the lighting here. R and theta, r tells me how far away from the pole to go, and theta tells me in what direction do I travel. So I'm going to start with the r equals 5 here. So if I start at the pole, each circle that we see represents 1 unit away from the pole. So this first circle would be radius 1, the second circle here would be radius 2, 3, 4, 5, and 6. And if you need more tick marks than that, you can always say the first circle counts as 2, the second one counts as 4, and so on. It can be pretty flexible like that. If you want polar graph paper of your own, you can always Google polar graph paper. That's all I did. It comes up with various different sites where you can download your own graph paper. So say I want to graph this point. We already know we want to go 5 units away from the pole. Next thing we want to do is figure out what direction. So theta is 7 pi over 4. I'm going to label my angles in standard positions. So I'll start with the quadrantal angles that we're all used to. So 0, pi over 2, pi and 3 pi over 2. And you'll notice that there are 1, 2, 3, 4, 5, 6 angles measured out between 0 and pi over 2. So if you do the math there, you can verify to yourself that each branch that we have here is pi over 12 radians. So we've got pi over 12. This is 2 pi over 12 or pi over 6, 3 pi over 12 or pi over 4, 4 pi over 12 or pi over 3, and so on. So if I look at my multiples of pi over 4, and that's really what I'm interested in here. So pi over 4s are going to be the midpoints for each quadrant. I'm going to get 7 pi over 4 out here in the fourth quadrant. And if I want to plot my 0.57 pi over 4, I'm going to go in the 7 pi over 4 direction, and I'm going to count how many units do I want to go. I'm going to count 1, 2, 3, 4, 5 units. So there's my point. So my point 5 comma 7 pi over 4. Now if I want to find the Cartesian coordinates or the rectangular coordinates that go along with this point, I can always go back to those relationships that we found in Theorem 11.7. So for instance, I can remember to myself, what do I want to remember to myself? I want to remember x equals r times the cosine of theta, y equals r times the sine of theta. And if you remember what cosine and sine of 7 pi over 4 are, cosine of 7 pi over 4 is going to be 1 over root 2. And sine of 7 pi over 4 is going to be minus 1 over root 2. So the x and the y coordinates are going to be r times the cosine theta, r times the sine of theta. So if the problem asks you to convert this polar point into a rectangular point, I can say that this is going to be 5 over root 2, comma, negative 5 over root 2. And that's in rectangular coordinates. I don't think you'll see that notation standard in your book, but generally it'll be pretty clear when you're talking polar or rectangular, but this is a way you can keep it straight to yourself as you're going through your notes or just trying to show your work to yourself. Alright, so with that example behind us, let's take a look at one more here. So if I want to graph the point 2 comma pi, I would suggest going ahead and pausing the video here and just seeing if you can do that on your own real quick. And if we want to do that, remember 2 is my r, pi is my theta. So if I just label my quadrantal angles here, I don't really have to do any more than that. Just labeling the quadrantal angles, I can say, okay, I'm going in the pi direction, so I'm going to go 2 units in the pi direction, and there's my point. Alright, so I'm tempted to say, are there any questions on that, but this is a video, so obviously you can't really in real time ask me any questions, but feel free to email me or ask me during a virtual session, whatever you're most comfortable with, and we'll make sure we get all your questions answered. Alright, so I'm going to use this 0.2 pi to illustrate something that's a little bit annoying about polar coordinates. Same thing that's annoying about trigonometry in general is that there are so many different ways to represent an angle. Likewise, in polar coordinates, there are many different ways to represent a point. There is no rule that says that my angle theta has to be between 0 and 2 pi. So 2 pi in polar coordinates represents this point that we just graphed right here, but I don't have to name it 2 comma pi. I can also say this is 2 comma negative pi, right? Because if I start at 0 degrees or 0 radians and I rotate clockwise by pi radians, clockwise by pi radians is going to get me the same direction as counterclockwise by pi radians. So 2 comma negative pi is going to give me the same point as 2 comma pi. And as you might expect at this point, any angle that is coterminal with pi radians is going to give me an equivalent point. If I do 2 comma any angle, so 2 comma pi plus 2 pi k, where k is an integer. So 2 comma 3 pi, 2 comma 5 pi, 2 comma negative 3 pi, any of those points in polar coordinates will land me at the same mark. Now, it actually gets even a little bit hairier than that, because there's no rule in polar coordinates that says that this number has to be positive. I'm going to go down one spider web here, and let's talk about, I'm talking about a negative number here, so I'll switch to red real quick. We'll talk about the point negative 2 comma 0. Alright, so if I look at my quadrantal angle, 0, pi over 2, pi, and 3 pi over 2, I'm traveling in the direction of 0 radians, so I'm traveling this way, but I'm going negative 2 units. Now, what does that mean? If I'm going negative 2 units in this direction, what that means is I'm actually traveling 2 units in the opposite direction. So instead of traveling 2 units in the 0 direction, I'm going to go 2 units in the opposite direction to that. So I'm going to go 2 units in the pi direction. And you can see that this gives me the same point as the one that we were looking at just a moment ago. So 2 pi can also be represented as negative 2, 0, which can also be represented, as you might expect at this point, as negative 2 comma 2 pi k, where k is an integer. So any point in polar coordinates has infinitely many representations. And that's one thing that makes things just a little bit more challenging than they otherwise would be. So let's take a look at another example. And what I'd like to do, I'm going to look at problem 27. And what problem 27 is asking for is it's asking to convert from polar into rectangular coordinates. So I'm converting the point 6 comma arctan 2 into rectangular coordinates. So I've got 6 comma arctan of 2. This is in polar, and I want to convert that to rectangular. Alright, so the thing that makes this a little bit interesting is the fact that we've got arctan of 2 here. It's not one of our normal reference angles. But let's take a look at how we want to do this. So I'm going to start by remembering what arctan of 2 is. So arctan of 2 is going to be the angle in quadrant 1 or quadrant 4. Technically, it's the angle in negative pi over 2 comma pi over 2, whose tangent is 2. Tangent is positive 2, so that tells me that my angle is going to be in quadrant 1. Tangent is positive in quadrant 1, it's negative in quadrant 4. So I know my angle is going to be somewhere in here. and tangent is opposite over adjacent. So I'm going to have a point that looks like that. Now I have to be really careful because what I'm looking at is not going to be the point 1 comma 2. Really, I shouldn't have labeled this quite like so, although it is tempting to do. I'm going to leave this in just so you can see that that is a temptation we want to avoid. What I really want to say is that this is 6. This I do know. If this is my point, then I've got the number 6 here, because that is my distance from the origin. My angle here is the arctan of 2. Now, opposite over adjacent is 2 over 1, but I don't know exactly how long this is or how long that is. I don't know that this is 1 unit and this is 2 units. In fact, I can show you that's not the case, because 1 squared plus 2 squared, if I think about the Pythagorean theorem, that obviously does not work. But what can I say instead? I know that this is going to be some value, and if tangent of theta is y over x, I know tangent of my angle is 2, right? Angle was the arctan of 2. So I get a nice relationship between x and y. I know that 2x has to be y, or I know that y equals 2x, right? So if I want to find what x and y are, I can use this together with the Pythagorean theorem to say that x squared plus y squared equals 6 squared, and then I can substitute in my 2x for y. Just be careful to put parentheses in where you're substituting. So 2x, the quantity squared, is going to be 4x squared. So a little bit of math here. 5x squared is 36. So that's going to give me x squared equals 36 over 5. So x is going to be plus or minus. Now, if I'm square rooting both sides, I need that plus or minus. But if I think about what the sign has to be, remember I'm in the first quadrant, so x is going to be a positive 6 over root 5. And y is going to be double that, so y is going to be 12 over root 5. So my point in rectangular coordinates is going to be 6 over root 5, comma, 12 over root 5. 6 over root 5, 12 over root 5. And that's in rectangular. Again, this R is not standard notation, but I think it probably helps us sort things out as we're looking through our notes. Now there are some other interesting applications in this section regarding converting equations. So if we convert equations from rectangular to polar or from polar to rectangular using the relationships that we've talked about. So remember, we've got the Pythagorean theorem, tangent of theta, and then the relationships between x r and theta and y r and theta. we can convert equations from rectangular to polar or from polar to rectangular. So some equations we'll see are easier to represent in polar coordinates. Some equations are easier to represent in rectangular coordinates. So just to start with a real simple example, this is number 64 in your book. Let's say we want to convert x squared plus y squared equals 25. This is an equation in rectangular coordinates. We want to convert this into polar coordinates. And you might remember from college algebra that x squared plus y squared equals 25 is a circle centered at the origin, radius 5. And if that does not ring a bell, you want to review section 7.2. That's something that we typically talk about with the distance formula. So that's where you'll find that topic in your book if that's a little rusty. In any case, we want to convert this to polar coordinates. And this is a really straightforward example. I can just say instead of x squared plus y squared, I can substitute in r squared for x squared plus y squared. So I'm going to get r squared equals 25. And I'm going to take the square root of both sides, and I'm going to say r equals plus or minus 5. And I'm actually going to wave my hands just a bit. You'll find this is kind of a recurring theme in polar coordinates, a lot of hand waving. I'm going to convert this simply to r equals 5. I'm just going to drop the plus or minus. Now, why can I do that? Well, again, if I think about how polar coordinates are represented, say I've got my circle. So this is my circle, r equals 5. Any point in polar coordinates with a negative r value, so let's say I've got the point negative 5, 0 right here. Take a moment and pause the video and see it. Make sure you can recognize how I labeled this point negative 5, 0 in polar coordinates. Any point can also be written with r as the opposite sign if I flip the direction. So negative 5 in the 0 direction is the same as 5 in the pi direction. Likewise here, this can be thought of as the point negative 5, pi over 2, or 5, 3 pi over 2. The fact that we can represent polar coordinates in many different ways allows us to simplify equations a little bit more than what we normally would be able to. So this is an example of an equation that is easier to represent in polar coordinates than in rectangular coordinates. So a circle of radius 5 centered at the origin has a very simple polar equation and has a slightly more complicated equation in Cartesian coordinates. So just for an example where we see things the other way around, problem 66 in your textbook, problem 66 in your textbook, we're looking at y equals 4x minus 19. And I want to convert this into polar coordinates. Now, from prior algebra class, you recognize this as a line, slope 4, y-intercept negative 19. If I want to convert this into polar coordinates, I'm going to replace the y and the x by expressions with r and theta. So I'm going to use y equals r sine theta and x equals r cosine theta. Now, typically when you represent an equation in polar coordinates, typically you want to get r by itself if possible. So what I'm going to do is I'm going to swing the minus 4r cosine theta to the left-hand side. I'm going to get everything on one side of the equation that has an r in it. Everything else stays on the right-hand side. I can factor out an r. So our quantity sine theta minus 4 cosine theta equals negative 19. And then divide everything through by sine theta minus 4 cosine theta. And there is my line in polar coordinates. Now I think most of us would agree that the equation in polar coordinates is more complicated because it involves some trig functions than the corresponding equation in rectangular coordinates. So that's the kind of thing you'll see. Some figures have easier equations in polar coordinates, typically circles, things that we can describe by distance from the origin. This is more conducive to polar coordinates. A line is going to be more conducive to rectangular coordinates. Now, these were two examples going from rectangular to polar. Going from polar to rectangular can be a little bit trickier. So if I go ahead in your book, I'm going to look at problem number 81. So problem 81, theta equals 2 pi over 3. And I want to convert this into rectangular coordinates. So if I think about theta equals 2 pi over 3, if I think about all the points that satisfy this equation, I'm looking at all the points that are in a 2 pi over 3 direction. 2 pi over 3 would be in this direction. So if you think about all the points that fall in this direction, all those points look like a line, don't they? And likewise, if I consider points in the fourth quadrant, this would be the 5 pi over 3 direction, but remember, any point in the 5 pi over 3 direction, I can rewrite this with a negative r value and change this to a 2 pi over 3 direction. So anything that's got a theta value of 2 pi over 3 is going to lie on this line. So I would expect to get an equation that looks like a equation of a line in rectangular coordinates. So let's see if that happens. So theta equals 2 pi over 3. How do I relate theta with y and x? Well, I look back at my equations and I remember that the tangent of theta equals y over x. So I know that tangent of theta is going to be tangent of 2 pi over 3. So y over x is going to be, now what's the tangent of 2 pi over 3? That's going to be one of my reference angles, right? So if I think about what the tangent of 2 pi over 3 is, my reference angle here is going to be pi over 3, or 60 degrees, so square root of 3, negative 1. So tangent of 2 pi over 3 is going to be negative root 3. So if I multiply both sides here by x, I'm going to get y equals negative square root of 3 times x. And lo and behold, that is the equation of a line through the origin. We've got a negative slope like we would expect for this line. So everything looks good there. Now let's take a look at one other example here before I let you go. Let's take a look at number 96. So 96. I'm going to look at r equals 1 plus sine theta. Now you haven't seen this yet, but we'll see this in section 11.5. 1 plus sine theta is going to be a graph that we look at in the next section. But I picked this one because it's difficult to know exactly what to do if we want to convert this into rectangular coordinates. So what can we do here? I'm going to go ahead and look back at what we have. We have a good way of relating r squared with x and y, but I don't have a real good way of relating r by itself with x and y, unless it comes with a cosine theta or sine theta. Now, I don't have an r squared, so what I can do is multiply everything through by r. And that's going to allow me to use that r squared equals x squared plus y squared, and r sine theta equals y, but it leaves me with this stray r here. So what I'm going to need to do is move everything that does not have an r in it to the left-hand side. So I'm going to move the x squared plus y squared minus y to the left-hand side, set it equal to r. Now I'm going to square everything here. And r squared, I can write that as x squared plus y squared. Right, so that was definitely a more complicated example. This is definitely something that looks nicer in polar coordinates than it does in Cartesian coordinates. So no surprise why we're studying equations like this in the next section when we already have polar coordinates at our disposal. So with that, that and the videos by the College Credit Plus instructor that I posted should be enough to get you started on WebAssign. Please let me know if you have questions.